Welcome to this lesson on containers. I'm going to talk about what containers really are and the function of these containers. What do they mean? What do they do? So I'm going to try to answer this in this particular lesson so that you have a solid understanding and a fundamental concept of containers. And they're very important when we start working with the Google Cloud and scalable applications. For example, these containers, or the term itself, plays an important role. So what is a container? Containers are a solution to the problem of how to get software to run reliably when moved from one computing environment to another. Okay, so that's a pretty straightforward definition of what a container is. So think of container as a box. So you create a software program, right, or an application with millions of lines of code, and you're not the only developer. There are certain other developers as well that are involved in creating this application, and now you want to be able to move the application from one environment, which is your test environment, for example, and then deploy it online. Okay, so you would need a container to do that. This could be, again, from a developer's laptop to a test environment, from a staging environment into production, and maybe from a physical machine in a data center to a VM or a virtual machine in a private or public cloud. So again, keep this in mind. Think of a container as a box, right? So you want to ship something out, you package it in a box, and then you send it out. Now, Google has been developing and using containers to manage applications for over a decade. In fact, everything in Google is a container. Okay. Here I want to talk about the differences between a virtual machine and a container. From this particular graphic on the left side of the screen, notice the VM has a physical processor, and then of course on top of the stack you have the virtual processor, operating system, libraries, and user code. On the right side, containers function a little differently. So you can see the difference where the shared aspects are between the operating system, virtual processor, and physical processor within this stack of a container. So containers are essentially less overhead as compared to virtual machines. So think of this as, with this particular virtualization technology, the package that can be passed around is a virtual machine, and it includes an entire operating system as well as the application itself. Now, a physical server running 3 VMs, for example, would have a hypervisor and 3 separate operating systems running on top of it. Okay? On the other hand, or by contrast, a server running 3 containerized applications, as for example like Docker apps, runs a single operating system, and each container shares the operating system kernel, which means the containers are much more lightweight and use far fewer resources than virtual machines. So a little technical definition of the differences between virtual machines and containers. Okay, so the important point to keep in mind is that containers have less overheads. That's why Google uses containers for all the apps. And in fact, Microsoft now, in their nano servers that are coming up, are including these containers in that technology. So since 2004, there was limited isolation, and then we released the C groups for these apps and released the LMCTFY, and then finally the Kubernetes, which is in, again, 2014, is what and how Google and the container technology has evolved over these years. And of course, in this course, I'm going to focus primarily on Kubernetes, and I'll talk about what that is. So I don't want to divulge more into it in this lesson. My focus here is to talk about containers. So containers at Google primarily developed as the only practical way to manage Google's scale compute, because you just imagine the processing and the data centers and the apps that Google runs. So everything at Google runs in a container, as I mentioned earlier. And Google launches over 2 billion containers per week. Okay, just imagine. That's a phenomenal number of containers every week, 2 billion. So we can see the benefit of these containers, right? They contain less overhead, you can scale applications and so on, and we'll get into that a little later as well. So why use containers? What's the problem? What's the issue? Why, in fact, do these containers came into existence? So the problems primarily arise when the supporting software environment is not identical. For example, let's say you're going to test using Python 2.7, and then it's going to run on Python 3.5 versions in production, and something weird will happen. Or you'll rely on the behavior of a certain version of an SSL library, and another one will be installed. Another problem could be the network topology itself might be different. You may have two separate network topologies that you want to move apps from one to the other. Or there may be security policies and storage might be different, but the software has to run on it. So today we have a distributed environment, and we have different hardware, we have different topologies. Each environment is unique in a sense. So what's the solution? The solution is using containers. So let's see how they solve problems. A container consists of an entire runtime environment for the app. So for example, an application plus all its dependencies are also included, libraries and other binaries, and configuration files needed to run it are all bundled into one package. Just like I mentioned earlier, just think of this as a box, right? So you order something and the delivery guy comes to your place and hands over a box to you, and that box contains an application, dependencies, libraries, binaries, and all the files all into one package. So by containerizing the application platform and its dependencies, differences in operating system distributions and underlying infrastructure are abstracted away. So that's exactly how containers solve problems. I'm going to talk about benefits of containers quickly in the next few slides before I end this lesson. So, foremost, reduces complexity through container abstractions. Containers don't really require dependencies on the application infrastructure. Therefore, you don't need a complex native interface to deal with platform services. Some other benefits are that they provide enhanced distributed computing capabilities, such as scalability. Applications can be divided into many domains, all residing within containers. The portability aspect, which is pretty important of these containers, means they can execute on a number of different cloud platforms. This allows engineers to pick and choose the platforms they run on based upon cost and performance efficiencies. And finally, a few more benefits: that they are a standard way to divide applications into distributed objects or containers, and we can break applications up this way, offers the ability to place them on different physical and virtual machines in the cloud or not. And this is important because today softwares are huge. There are millions and millions of lines of code, unlike the conventional method of creating softwares. Today we need multiple developers, and these individuals are spread all across the world. So they're not sitting in one room and developing applications anymore. So containers provide a seamless way to benefit these softwares. And this flexibility offers more advantages around workload management and provides the ability to easily make fault-tolerant systems. So again, think of this as diversification. And also, with the use of clustering, scheduling, and orchestration technology, developers can now ensure that applications that exist inside the containers can scale and are resilient. These tools can manage groups of containers using a well-defined container management layer that provides these capabilities. So, in conclusion, we talked about in this brief lesson what is a container, so you understand what a container is. Think of this as a box that contains all of the elements of the software or the application, right? The binaries, the actual package itself, all the related files, the dependencies, and so on. We also understand the concept and the difference between virtualization and containers. Containers seem to be more portable and bear less overhead. And we talked about various issues in applications, like why do we need a container, right? So we talked about the need of using containers and how do containers solve these issues. And of course, lastly, we also mentioned the benefits of containers. So I hope this lesson simply provided you a solid understanding of knowing what a container is, the difference between container and VMs, and the real issue and the solution that these containers provide. So I hope this helps. But before I end this lesson, let me switch to the Google platform here, and I'm going to show you on the Cloud Console where this container engine is. So once I'm logged on to the Google Cloud Platform, for example, let me navigate to the products and services. And if I scroll down under the compute section, notice there's an option called Container Engine. Okay, so let me go ahead and click on this, and this takes you to the container clusters that we can create, and of course we can also work with the container registry. So what are these clusters? Containers package an application, just like I talked about, so that it can be easily deployed to run in its own isolated environment. Containers are managed in clusters that automate VM creation and maintenance. So there you have it. Within the Google platform, we can take a look at the container engine, and of course I'll demonstrate in subsequent lessons how to go about creating these clusters and working with the container engine itself. So practice, and let's move to the next lesson.